Alright guys, let's get started. Earth Science, Chapter 3, Models of the Earth. What are we going to be looking at in this particular chapter? We're going to be primarily focusing on maps, mapping technology, different mapping terms, things like that. It's a pretty easy chapter. A lot of the stuff we're going to be doing with this, we're going to be doing in class with diagrams, with labs, with various things like that. A lot of this is very hands-on learning, so most of what you guys are going to be getting today is lots of definitions, lots of overviews, lots of different things like that. So let's jump straight into it. Very first thing, how do we map out the Earth? Well, because it's a spherical object, we map out using a coordinate system. This particular coordinate system is driven by two different sets of lines or vectors, or however you want to put it. One is latitude and the other is longitude. You've probably heard these before. Latitude basically separates out the Earth and its equator from the Earth and its poles. And the different lines represent how far away from the equator that you happen to be on any particular portion of the Earth. On your notes, your definition is as follows. Latitude is the angular distance north or south from the equator, and it's expressed in degrees. You can get all the way from 0 up to 90 north and 0 to 90 south. And you'll notice that after each number, it's noted with an S or an N, north or south, and then the degree sign that goes with that. So the other thing here is that we also use the term parallel. Any circle that runs east and west around the Earth and is parallel to the equator, and it's a line of latitude. So once again, you'll notice here's our equator, and these are parallel lines. They do not run into it, they run along it, parallel lines. So sometimes we call these parallels. So we might say the 15th north parallel or the 30 north parallel. Okay. Let's keep looking at a couple of things here. On your notes, it says the zero line is located at the equator. Above the zero line is north, and below the zero line is south. Okay. Let's talk about some of these degrees and what do they mean. We said before that it goes all the way up to 90 degrees, right? Latitude is measured in degrees. The equator is 0. The latitude of both the north and south pole is 90. In actual distances, 1 degree of latitude equals about 111 kilometers. That's a pretty decent distance. That's about the distance between here and Denver. That's quite a bit. And because it's such a huge distance, sometimes scientists want to break that down into a little bit smaller units. It's kind of like with feet. Why do we have inches with feet? Well, because sometimes we want to measure something that's smaller than a foot. So when we want to measure something that's smaller than 1 degree, we'll do it in minutes and seconds. It can get a little bit confusing, but this has nothing to do with time. It's a measurement of distance. Okay. Each minute, each degree of latitude consists of 60 equal parts called minutes. So 60 minutes makes 1 degree of latitude. That means that each minute is about 2 kilometers or so, and it's called minutes. And then 1 minute of latitude equals 1.85 kilometers, about 2. And then you can take each of those minutes and divide it into 60 equal parts again, called seconds. And they get smaller and smaller and smaller. I think these symbols are a little bit off. I think it's minutes and seconds. I'm not 100% sure. We'll talk about it in class. I'm not sure where those symbols came from. But let's keep going. Over on your notes, you'll notice it says A blank, that's degrees, 1 degree. 111 kilometers equals 1 degree. The number of degrees between the equator and the poles is 90. B is minutes. 1 degree equals 60 minutes. And C is seconds. 1 minute equals 60 seconds. All right. So that's one of the measurements. We said before that there are 2 of them. So this is one of them, and it goes along the equator. The other one goes up and down. So this one went side to side. This one goes up and down. This one's called longitude. The zero line for longitude is located directly in the country that founded and figured out this mapping system. Any guess as to which country that is? Yep, it's England. They figured all this stuff out. So they got to set zero wherever they wanted to. Whereas before, the equator kind of made sense because it was a literal geographic location, and the equator was where the sun was overhead the most and where it's the hottest. This particular system that goes east to west could have been located anywhere on the surface of the Earth, but the British basically founded this particular system of navigation, and it's the system the entire world uses, so they set the zero line right here in Great Britain. If it had been discovered in America or in Asia, the zero line would be in one of those two locations. Now, what else do we see here? We see the zero line is there. This direction is west, and this direction is east. And in fact, we name a lot of our places and a lot of our locations and a lot of our cultures based upon this east-west designation. Have you ever heard of Western culture versus Eastern culture? Well, what is Western culture? Western culture is everything on the west side. So that includes places like the United States, Canada, Mexico, Australia, a little bit of South America. What about Eastern culture? China, Russia. Have you guys ever heard of the Middle East? The Middle East is over here. Why is it called the Middle East? Because it's kind of in the middle of the eastern area. It kind of makes sense. So let's talk about that. Longitude. What is its definition? Longitude's definition is the angular distance east or west from the prime meridian. That zero mark there, we call it the prime meridian. Okay, so east or west from the prime meridian expressed in degrees. How big can that get? Well, it can go all the way from 0 to 90, and it looks like it goes to 90, but in reality it actually goes to 180 because it goes all the way around the Earth to the opposite side of the Earth. And that opposite side, you probably have heard of it before. It's called the International Date Line. It's where the days are actually a little bit different because we have time zones and things like that. So you can go on this western side 180 degrees all the way around, and on the eastern side 180 degrees all the way around. And what does that add up to? 360. And that's the distance around an entire circle. Okay. So now, on your notes it says the number of degrees from one side of the Earth to the opposite side is 180. And it also says the zero line is located in England. It's called the prime meridian. This is the zero line. It's located in England. To the right of the zero line is east, and to the left of the zero line is west. Once again, I'm going off of your notes right now. You should be following along with me. The 180 degree line is located in the middle of the Pacific Ocean. It's located in the middle of the Pacific Ocean. And what is that 180 degree line called? Sometimes it's called the International Date Line. It might also be called the anti-meridian, meaning like the opposite of the prime meridian, the anti-meridian. Okay. We're going pretty fast here. Let's keep going. Great circles. A great circle is any circle that divides the globe into two halves. Great circles are kind of like a human way of measuring the Earth. It's a human way of dealing with the geometry of the Earth. There's only a handful of great circles out there. The equator is one great circle, and then all of these up and down lines are also great circles. Basically, any line that would cut the Earth into two perfectly equal halves is a great circle. What about this line here? That one. Will that one, if we cut along it, cut the Earth into two halves? No. So is it a great circle? It is not. Okay. The equator is the only latitude line that's a great circle. All of the longitude lines are great circles. So all the longitude ones, if you cut along any of those, you can cut the Earth in two perfect halves. But the latitudes, if you cut along any of these, except for the equator, you won't cut it in perfect halves. So the equator is the only one that is a great circle. Let's keep going here. GPS systems. How do GPS systems work? What do we use them for? So on and so forth. You've probably heard of GPS before. GPS stands for Global Positioning System. Global Positioning System is how we find our way around the Earth. GPS is usually a satellite navigation system that's based on a global network of satellites, and they transmit radio signals all over the surface of the Earth. We can tell where we are based upon where the satellites are and where we are related to those satellites. We do it through a process called triangulation, where three separate satellites effectively figure out how far away we are from them, and their distances overlap at only one location. So it's kind of like a Venn diagram, where the Venn diagram only overlaps in one location because these satellites, they cannot actually tell the direction that a radio wave travels from. So when you ask a satellite, hey, where am I? One satellite will not be able to tell you where you are. It'll tell you how far away from it you are, but not where. So it could say, oh, you're 100 miles away. Well, 100 miles away is a big circle around that satellite. And then this satellite says you're 200 miles away, and it has a big circle around it. This one says, oh, you're 150 miles away, and it has a big circle around it. Those circles will only overlap in exactly one location. And when that happens, you're able to figure out where you are. Map projections. What are they? What do they do? Well, we as humans have a particularly kind of interesting problem. The Earth is round, but our maps are flat. Anybody see the issue with this? Yeah, if our Earth is round and our maps are flat, they won't match up well. Literally, let's say, for example, I gave you a globe, and I wanted you to cut the globe into pieces so that it would lay flat onto a table. You'd have to make a tremendous number of cuts to make it lay down perfectly flat. And even then, it's still going to have waves and ripples and all sorts of other problems with it. So what do we do in order to deal with this? Well, we create something called map projections. Map projections are basically flat representations of a round object. So the round object is the Earth, and the flat representation is our map. What we try to do with these maps is we try to make it so that they show us some areas of the map in greatest detail and other areas of the map in less detail, so we kind of have an idea of where the map is the most accurate. Maps like these are made by taking a piece of paper and wrapping them around the Earth in different ways. One way is shown here. You can wrap the map around the Earth all the way around. You could also wrap your map around the Earth like this, where you just put one particular piece of your paper directly on one piece of the Earth and you draw what you see. Another way is to take your paper and turn it into a cone and wrap it around the Earth. Each one of these has different strengths and weaknesses. The main strength and weakness of maps like these is that they are most accurate where your paper is closest or touching the globe, and they are least accurate where your paper is not touching. So this first one, on your notes it says types of map projections, A, B, and C. The first one is called a cylindrical projection. Where is this map most accurate, you think? It should be most accurate around the equator, because that's where the paper's touching. Where is it least accurate? Up here near the poles, where it's not touching. So we would see the greatest accuracy right here in the equator and the least accuracy up here. And what happens when a map becomes least accurate? Well, usually what happens is that different parts of it become enlarged or bigger than they actually are. So for example, here you might see this. Greenland looks bigger than the United States. But is it? Not really. Greenland is actually pretty small. It's smaller, it's about the same size, if not a little bit smaller than the United States. But it looks big. Same thing with Canada, same thing with Russia. This is one reason why people think Russia is such a colossal nation, and while it is pretty big, in reality it's not as big as people actually think. Another one up here, this one is called azimuthal projection. most accurate in the middle, least accurate around the outsides. Okay. And the last one is called a conic projection. And this one actually does a little bit better job. Do you notice here? Greenland doesn't look as big as the United States in this one, does it? It looks a little bit different. That's because each of these maps does a different thing. Let's move on. Skipping that one. Symbols, reading maps, all that kind of stuff. We're going to go over this in class. We're not talking about it in a lecture video. Scale. Scale is an important one. Scale is the representation between the distance shown on a map and an actual distance. It's kind of like an inch on a map equals 1 mile in real life. Usually they'll have a little scale on the map that tells you how big that map is compared to real life. So for example, this particular map here, it says here 0 and 6 miles. Now this map is not 6 miles big, but this distance on this map represents 6 miles. That's important. Okay. Another couple of things here. On your notes, it says important map parts that I want you guys to be aware of before you come to class. One of them is called an isogram. An isogram is a line on a map that represents a given value or quantity. Okay. Isogram. So gram can be changed to describe the measurement being graphed. So let's say, for example, we're looking for lines of equal temperature. We'd say an isotherm. If we were looking for types of equal pressure, we'd say isobar. Okay. We can change that, but iso basically means line of same. So line of same. So what do these lines look like? Well, you're probably familiar with them. Like this. This is a topographical line. This one shows height. So, or height above sea level, or height below sea level, or various other things like that. In this case, this one says actually solar radiation. So this one tells us how much solar radiation each one of these areas is getting. And the line tells us what's happening in those areas. So everything between 300 and 350 is getting a number between 300 and 350. Everything between 350 and 400 is getting a number in between there. There aren't going to be any 5, 6, 700s in here. It's going to be 350 to 400 because change happens gradually over a given location. Okay. Well, let's continue onward. Topography in a topographic map was a topographic map show. Topography or topographic map shows the size, the shape of the land surface, the region including its relief, basically how steep it is or how flat it is. Okay. On a topographic map, they oftentimes will have contour lines. A contour line is a line that connects points of equal elevation. So if a particular ridge line is all 500 feet above sea level, that ridge line is going to be outlined with a line that says, hey, it's above 500 feet above sea level. And as it goes up, there's going to be a line above it that says 600, and a line above that that says 700. And typically, the farther apart the lines are, the flatter the area is. The closer the lines are together, the steeper an area is. On the notes, it also asks you what a relief is. A relief is the difference between the highest and lowest elevations in a given area. So let's say, for example, you're looking at a map of a mountain, and that mountain goes all the way from 0 to 1,000. The relief would be 1,000, because that's the difference between 0, the lowest point on your map, and 1,000, the highest point on your map. There are a couple other maps that we will probably be looking at. One is called a geologic map. Geologic maps show geologic areas. They show geologic features, rocks, major plate tectonics, and things like that. Usually a geologic map is heavily colored, and it looks like this. So all these different colors here represent different types of rock. You'll notice that a lot of these colors are in big swath areas, like a whole big area of swath of red there. That might represent one particular type of rock that's there on the surface. You'll also notice here in the mountains, if you look real closely, you'll see lots and lots of different colors. Why do you see so many different colors? Because as the mountains are destroying and building up new rock, they expose new things. So you'll see a little bit of ocean rock here, a little bit of plains rock there. You might see a little bit of desert rock over here, and it's all smashed together because of the mountain building process. The last particular type of map we'll talk about is a soil map. A soil map basically covers the different types of soil. It talks about whether or not it's sand, silt, clay, things like that. We like to use soil maps especially for farmers, for builders, and for pretty much anything human related, because soil maps are going to tell us a lot more about things like, hey, is there water underneath of our feet? Is this a place that's going to be good to build, or are we going to experience landslides? Is the ground underneath of us going to shift? So on and so forth. Is this a good place to build crops? Things like that can usually be shown by a soil map. Soil maps look a little bit like this. Once again, very, very colored. Once again, they show individual areas and they say, hey, these are all the different types of soil. They each have their own special little name because they're deposited by special little streams that have their own special little compositions. And people can use these to figure out which areas they want to buy, which areas they want to build on, which areas are going to be nice and consistent and easy to build on. Are we building on sand or are we building on clay? You typically don't want to build anything on clay. The clay is expands and contracts and it breaks apart foundation. Sand is usually pretty decent to build on. But sand is not the best thing to farm on. You can, but it's not the best. Yeah. So, with that said, we will be going over different things in class related to mapping. We'll be having activities, games, things like that. This can be one of the more boring chapters, so we have a lot more games with this one. Don't forget to look at the videos that are included in this particular activity. And that's pretty much it. So, I'll see you guys in class.